So welcome everyone for today's webinar. So we are talking about simulation of electric motors in COMSOL Multiphysics. So let's jump into that section. So I'm the presenter here, and just before we go into the details, let me show you the agenda. So I will talk a little bit briefly about COMSOL Multiphysics. What is it and what kind of solutions does it offer to your needs, and what kind of electric motors and how you can simulate electric motors in COMSOL Multiphysics, what is geometry parts, how it fits in your modeling workflow, different boundary and material properties. I will talk a little bit about those, what we used here in this simulation part, what kind of study settings do we apply here, and I will go into COMSOL Multiphysics to do the live demonstration part, and we will have a Q&A session after that. Just a few words about COMSOL. So core COMSOL can model linear physics like heat transfer, convection, laminar flow, linear structure mechanics, and physics is grouped into four bigger branches: electromagnetics, fluid and heat, structural and acoustics, and chemical. And today we will touch features from the AC/DC module and the heat transfer module. So we will do a couple simulation to generate an efficiency map for an electric motor. And there are all multi-purpose modules like the material library or the optimization module. So if you have a parametric geometry, you can use the built-in optimization algorithms to further improve your design, to reduce, for example, mass or maximize the output power or torque, depending on your design needs. And we have the interfacing products like the LiveLink for Simulink and the LiveLink for MATLAB. So if you want to have a high fidelity model, like a finite element model of your electric motor with all the physics, all the proper physics setup, then you can attach this model in a co-simulation manner with Simulink, and you can build the controller part there, and you can do the co-simulation within the Simulink interface. And that's a very brief and short introduction what you can do with COMSOL Multiphysics. And let's talk about today's objective. So we will discuss how to compute losses in the iron and the copper part of the motor, and how to take into account temperature. So it can have a significant effect on the motor torque and on the efficiency also. And how to generate the efficiency map of that motor. So what sort of study steps we will apply here. So we will discuss the geometry, the different materials that we used here in the setup, other boundary conditions, and we will discuss the outputs. So what can we see in the results node? How do we get there? And how to achieve these distribution maps and efficiency maps inside COMSOL Multiphysics. So this is our current setup. So this will be our geometry that we will use here in COMSOL Multiphysics. As I mentioned earlier, you have the option to import the geometry from dedicated software, or you can use the built-in part library. That's a new feature inside COMSOL Multiphysics. So we will have different parts, the rotor and the stator part. It has different sections. We have the permanent magnets inside the geometry. In an internal geometry parts, which is parameterized, you can quickly investigate different setups. So let me go into our COMSOL setup. So here we have a geometry parts. For some of you, it may be new. And here you can import different sections from this library. So you can import internal parts like the rotor section, and it's parameterized. So you can change these parameters inside the geometry node. And you have also the external part, so it's already predefined. So where can we find these parts? So here, if you go to Windows, Part Libraries, here under AC/DC module, rotating machinery, rotors, internal. So you can see the built-in sections for the internal parts, and under stators external, you can see the external parts. So they are parameterized and we can import them to our geometry setup. And that's what we have done here to build up our custom model here. And they appear here under the geometry parts. So this is the geometry section here. So if we go back to our setup here and we continue with the materials and the constitutive relations, you can see here from this setup that different sections have different physical setups. So we have the magnets. They are set up in a different way. Then we have the coils. They are grouped into so-called coil groups. So you can define the different phases in this manner. And in the iron part, you can set up the BH curve and the different material properties. So let's see how does it look like in our model here. So if we go back to our COMSOL setup here, and we go into our component and under materials. So here we can see different sections. So we have domains where we have air defined, then we have the soft iron. You can see these are the domains that where we touch this part. And if we go into that section, we can see that the BH curve can be found here. So we can plot this also. So this is the typical BH curve that we will use for this simulation. If you have your own curve from a data sheet or from measurement, you can import into and create a custom BH curve. This one is from the built-in material library, but you can freely customize if you wish. These are the copper parts. This is the magnet section. These are the magnets defined here, and we have the shaft here, which has the relevant material properties here. So that's how we set up here. And under the physics, here you can see different sections have different boundary conditions. So these are the domains where we define the material with a BH curve. Then we have the magnets. This is one group in one direction of the magnetization. This is the other direction, other magnets with different magnetization direction. Then we have the phases. And this is for phase A, B, and C. So we have the three phases here. And we have different subnodes. And yes, one subnode added here is the current direction. So we can reverse to make sure that the current is flowing in the right direction. And that's the setup here for the material property side, for the magnets and for the other sections. For the mesh, so we did not do any special attention to create this finite element mesh here. So we used the built-in functionality from COMSOL, and when we have a continuity pair, so where the stator and the rotor part attaches, so when there is a sliding boundary condition, COMSOL will automatically create a very fine mesh to make sure that the solution is quite accurate over those domains. And we use the built-in features to calculate the torque that will be the result of this motor simulation here. Okay, so how to model temperature dependency. So most of the built-in materials have the functions, the properties that depend on temperature, like conductivity or density, but you can put your own function anywhere in COMSOL Multiphysics. So wherever you can click, you can put a custom function there, like here for the conductivity. So it can be a function of temperature, for example. So that's super easy to do that here. So that's what we applied here. And you can, with this, you can take into account the effect of temperature rise, so how it will affect the efficiency of the motor and the output torque of the motor. So under the material part, we can go there and we can define the functions there. It's quite easy to do that. So under the material property, so if we go back to our model here, so you can set up quite easily these functions. As you can see here, so we set up another function for the flux density of the magnets. So it has different values at different temperatures. And it's quite important because these magnets, these electric motors in a stationary section, it can heat up to 100, 120 degrees of Celsius. And with these temperature rises, we can have a 20–30% deflection of the flux density. So it can affect performance quite. So we cannot neglect the effect of temperature. And that's easy to do and easy to interpolate inside COMSOL multiphysics. So it's easy to add these custom functions here. So with that, we can include these effects quite easily. So as you can see here, so we have a custom function here for the conductivity also, not just for the magnets, but also for the coils. So yes, the conductivity is the function of the temperature. So it affects our performance. And going further with the boundary conditions and the material setups, so these are the different study types required to do the efficiency map and the motor torque calculations. So we have two different study nodes. Study one is for the magnetic calculations and to generate the efficiency map. And the second study is used for calculating the temperature distribution inside our motor. And just to name a few of these steps under these study solutions. So we have a parametric sweep and then we have a stationary sweep. So in the stationary solution, we calculate the magnetic field, then we create a time-dependent simulation. And this is required because we want to calculate the losses. And in the third step, which is the time to frequency losses, that's where we will apply an FFT on the solution to transfer the time domain solution into a frequency domain solution. So that's where we can calculate the losses inside the coils and in an iron parts. And for different parts, we can have different loss calculations. Our copper parts and our coil parts. So let me close this up. So here, so we have on the coil node here, and as we discussed, the conductivity is the function of the temperature, and also we can add the sub node here that you can see here. This is called the loss calculation. And from the model section, so for coils, we can use the resistive heating option here. So it will calculate the losses based on these equations. So this is the equation here. So that's how we calculate the losses in the coils in the different phases. And also we can calculate losses in the other regions. So these parts are defined with their corresponding BH curves. And here we have another subnode here, another loss calculation subnode. And here from the loss model, you can select the same as previously, which is the calculate the loss from resistive heating, or we have three other ones, the Steinmetz, the Bertolli, and of course the user-defined options. So whenever you have your own equation, empirical equations, you can put your equation there, or we can use one of the built-in models here, which is in this case the Steinmetz model. So that's what we apply here. And also, of course, another section, which is the torque calculation. So this is here, you can see this is the equation that we utilize to calculate the torque inside our motor. And we can compare this to the numerical solution as well. So from the physics side, so we have the BH defined regions, we have the magnets with different magnetization directions. And we have the three phases. There are two options. One is with linearized resistivity and one which is not using this section, which applies a constant conductivity, which is non-temperature dependent. And we have another subnode here, which is the moving mesh. So we have the rotating domain feature here. So the internal part, the rotor part, is defined as that can slide along other mesh elements. And from the heat transfer side, we have a heat transfer in solids section here. And solid goes for solid domains. And there is another one, which is a fluid one. So we have air also in the thin gaps, thin sections, and then we apply this fluid subnode section here. So this is the physics setup, the two different physics, which is for the AC/DC calculation, and the second one is used for the heat transfer calculations. And we can have different results, different sections here. One is for just to match whether the input and the output plus the losses equal. And here on the right-hand side, we can see the percentage error at the different speeds, the different rotational speeds, how they perform. So we can check the performance of the numerical computation, how accurate our calculation is at different stages, the different current excitations and the different rotational speeds also. And the same goes for the losses. So we can check what's the dependency of the losses, the iron and the copper losses on the rotational speed and on the excitation current, and how the torque is behaved and performing under different rotational speeds and under different phase currents. And we can check whether they match the empirical values here. From the heat transfer part, there are several options what you can do with the heat transfer module. So you can include external forced cooling, or you can include natural convection if you wish. So you can decide what is the maximum allowed temperature in your motor design, and you can design whether a passive cooling with fins, large enough ones enough, or you may need an active cooling for your current design. So you can take into account these effects as well. And these are a few snapshots with different cooling velocities. And as you can see, if we have only natural air convection, you can see on the leftmost figure, we have more than 162 degrees of Celsius. And if we apply some active cooling on our motor, we have much, much lower temperature distribution here. And we can take into account what's the effect on the motor torque, on the losses, iron and the copper losses, and on an output power. And as you can see here in the top right figure, in the top right corner, you can see that with the temperature rise, if we take into account the effect of temperature, how it affects the material properties, the magnetizations, and the conductivity, you can see this is the green line here. So we have much lower output power. So if we take into account the temperature rise in our motor setup. And so we will include these slides in the follow-up email, and you will have detailed setups how to set up the efficiency map. For simplicity, I will go over it and I will discuss only the results here. So here in the left-hand side, you can see the efficiency map without taking into account the temperature rise, the temperature dependency of the material properties like the conductivity and the magnetic flux density. So this is an analytical solution. So you can put this equation into COMSOL and you can generate this figure, what you can see here on the left-hand side. And here on the right-hand side, you can see the numerical solution that we map from the COMSOL solution. So here you can see the same efficiency map, and it matches quite well what we can describe with an analytical approach. So we can create the same efficiency map in COMSOL multiphysics. That's what you could do with with an analytical approach here. And this second slide shows the effect of temperature rise. As you can see, it's quite different that we have seen here in the previous slide. So here we have different shape and different sections of the efficiency map, but now we have taken into account the temperature rise on material properties. And you can see that we have much lower output torque, and the efficiency parts have moved away in our efficiency map also. So here, if we go into our COMSOL setup, we can see, and in the results node, we can examine these sections here. So this is the efficiency map without the temperature rise. So this is the solution of the numerical computation. And this is what we can achieve when we take into account the temperature rise also. So compared to that one, so you can see that at the maximum rotational speed, the efficiency is much lower, and also the output torque has decreased, and the shape of this map also changed a little bit here. So how to get there? So we created a parametric sweep. So we sweep the current and the rotational speed of the motor. Then, as I mentioned earlier, then we create a stationary solution for the magnetic parts. Then we create a time-dependent simulation where we can calculate the losses. Then this time domain solution is transferred to the frequency domain with an FFT. Then we can create another stationary solution for the heat transfer part, another time-dependent simulation, and another time to frequency to map the results into frequency domain. So that's for the efficiency map. And for the temperature distribution, we have almost the same steps like a stationary one, then a time dependent, then we turn from time domain to frequency domain. Okay, so this is our efficiency map that we can create here. And we can also plot the temperature map, how the torque and the speed relates to the temperature rise. So as you can see, the higher the speed of the electric motor is and the output torque that is required, then we get much higher electric motor temperatures. So it will rise to almost 200 degrees of Celsius here. So that's how we can conclude here. Okay, so just to wrap up, so with this model, you can easily calculate different scenarios for different motor speed with different driving currents with different material properties. So you can easily create an efficiency map for an electric motor. And since for this design, we know the analytical solutions for the efficiency map, for example, we can easily validate our solution, whether it matches that part or not. So we can fine tune our finite element model here. And we can also use the built-in geometry parts, the part library. So we can easily create parametric geometries. So we can fine tune our initial very first electric motor design to our needs. What could be the maximum allowed temperature? Do we need an active cooling or a passive one is enough? What should be the maximum allowable driving current and so on? So you can create a very nice and robust electric motor calculations here. So of course, we will hand out the models and the slides for you. So if you need any more questions, any more assistance for that, just feel free to contact us and we are here to help you.